Hello everyone, and welcome to this lecture. This lecture is a part of module 3 of your course in Mathematical Physics 3. And in this lecture I shall carry my discussion forward from my earlier lecture on Laplace transforms, where I had introduced the idea of Laplace transforms and how to use this notion to calculate Laplace transforms for some simple functions. In this lecture we shall explore some of the properties of the Laplace transforms, the linear property, the Laplace transform, derivatives, integrations, and so on. So we'll first start with a recap of what a Laplace transform is. So suppose I have a function f of t, then its Laplace transform is another function f of s. Okay, we are changing from one variable to another variable. We are going from a variable t to another variable s, and this transformation is via an integration. So that's why it's an integral transform, and we are integrating from 0 to infinity using a kernel function, and that kernel function is e to the power minus st, and we can write it succinctly as L of f of t. So L of f of t is the same as taking this integral, which will give us f of s, where s is real. And in the previous lecture we saw that there would exist some value, some real value s naught, such that this integral will exist whenever s is greater than s naught, and it will not exist whenever s is less than s naught. So our Laplace transform will be valid only within this region, not in this region. Okay, so first is the linearity property. Very simple. It says that the Laplace transform of a linear combination of functions equals the linear combination of the Laplace transforms of the functions. So let's say I am having two arbitrary functions f1 and f2, and there are two constants c1 and c2. Then if I take a linear combination of these two functions c1 f1 plus c2 f2, and then I take the Laplace transform of that linear combination, that is the same as taking the linear combination of the Laplace transforms of the individual functions. That is Laplace transform of f1 multiplied with c1 plus the Laplace transform of f2 multiplied with c2. So this is the linearity property, pretty basic. Then we come to the Laplace transform of derivatives. So suppose I have an arbitrary function f of t. Okay, then the Laplace transform of its derivative, so f of t, and its derivative is f prime t. So this f prime t is the derivative of this function f of t. Then the Laplace transform of this derivative is given in this way. So L of f prime of t is equal to s into Laplace transform of the original function minus the value of the original function at t equals 0. Okay, so Laplace transform of this derivative is s into Laplace transform of this function minus the value of this function at t equal to 0. So we can very easily prove this. We go by the definition of the Laplace transform. So moment we have L of f prime of t, this is equal to integration of f prime of t. Whatever is inside the bracket, that will be integrated after multiplying with e to the power minus st from 0 to infinity. So now how do we evaluate this? Okay, we can go fall back upon our integration by parts. Okay, so integration by parts, u prime v, integration of u prime v is equal to uv minus integration of uv prime. So if in this case I take here, it is very easy because we are looking for some function which has been differentiated. So here already f is been already differentiated, so we take f as u. Okay, so we take f as u. So here we have f prime, which is u prime, and v we take it as e to the power minus st. So we'll have f of t e to the power minus st 0 to infinity minus integration of uv prime. uv prime, u is f of t and v is e to the power minus st, so differentiation of e to the power minus st. So this is going to evaluate to f of 0. How? Because when we put the upper and the lower limits, so when I put the upper limit, as we saw in the previous lecture, we had discussed this, when I put the upper limit infinity on e to the power minus st, that is going to give us 0, because we have minus s, and of course this condition, this will be possible only if s is positive. So 1 by e to the power st, so when you put infinity, we have 1 by e to the power infinity. So 1 by e to the power infinity is 1 by infinity, which is going to give us 0. So the upper limit, which is infinity, that is going to give us a 0 over here. And the lower limit, the moment you put in a 0 here, so e to the power 0 is 1, and here we also will have a 0, and because it's lower limit, so there will be a minus sign, so we'll have minus f of 0. So minus f of 0 comes from the lower limit. Substituting the lower limit, the upper limit gives us a 0 already. Minus, okay, so differentiation of e to the power minus st is minus s e to the power minus st. Okay, differentiation of this is minus s e to the power minus st. So we have a minus sign here, which comes because of differentiation, and already there is a minus sign outside, so these two will give us a plus sign, and this s will come outside because you are integrating with respect to t. So s integration of f of t e to the power minus st dt from 0 to infinity minus f of 0. So now this we can recognize very easily. What is this? This is nothing but the Laplace transform of the original function f. Okay, so we can write it as s into Laplace transform of f of t minus f of 0. So this is the proof of this property, that is the Laplace transform of derivatives. Okay, so this is the Laplace transform derivatives. Okay, this is the Laplace transform of the first derivative, I should say, because this is f prime. We can again go one step further. Okay, we can find out the Laplace transform of the second derivative. So what we do is, we take this f prime of t, we take it as, we write it as g, because derivative of a function is another function. Okay, so f prime of t is going to give me another function. That function we call it as g of t. Then second derivative of this function f is going to be the first derivative of this function g of t. So f double prime t is equal to g prime t. So Laplace transform of the second derivative of f will be equal to the Laplace transform of the first derivative of g. And because here, if you look at this, I have said it's an arbitrary function, right? F of t is an arbitrary function. That means it can be any function. That means instead of f of t, I might as well use g of t here. So the same relation will hold good, right? So L of the Laplace transform of g prime t is equal to s into Laplace transform of g of t minus g of 0. So you can just apply this over here. So we have Laplace transform of f double prime t is equal to Laplace transform of g prime t, and Laplace, I use this same property here. So Laplace transform of g prime, so just replace f with g here. G prime t is equal to s into Laplace transform of g of t minus g of 0. So this is what we have here. So we substitute this back. What is g of t? G of t is f prime t. G of t is f prime t, and g of 0 we can write it as f prime of 0. Okay, so now f prime t, we already know what is f prime, Laplace transform of f prime t, it is s into Laplace transform of f of t minus f of 0. So we just expand this here, this Laplace transform of f prime of t, we just expand it like this. So we get s into Laplace transform of f of t minus f of 0. So we get Laplace transform of the second derivative of f to be equal to s square into Laplace transform of f of t minus s into f of 0 minus f prime of 0 for s greater than 0. This s greater than 0, we got it because of the integration. In the previous slide we had already discussed how we will obtain this, otherwise you will not get this result. So in general, we can write down that this is the second derivative of f. In general, we can obtain a relationship, an equation for the nth Laplace transform of the nth derivative of a function. So Laplace transform of the nth derivative of f is equal to s to the power n Laplace transform of f of t minus s to the power n minus 1 into f of 0 minus s to the power n minus 2 f prime of 0, and so on till the n minus 1th derivative of f, which is evaluated at t equal to 0. Okay, so this is what we have here. I mean, this expression is basically a special case of this. You put n equal to 2 here, n equal to 2, this becomes f double prime. This will give us s square, okay, L of f of t minus, you put a 2 here, 2 minus 1 is s, f of 0 minus, we put a 2 here, 2 minus 2 is s to the power 0, which is 1, f prime of 0. So the last term is n minus 1, that is 2 minus 1. Okay. Okay. So now we come here. Okay, let's take an example. Okay, where we can apply this. So the second derivative, Laplace transform of the second derivative is s square L of f of t minus s f of 0 minus f prime of 0. So now let's consider this function. Okay, sine of at. Okay, what will happen if I differentiate sine of at? When you differentiate sine of at, d by dt of sine at, this will give us a cos at, because you're differentiating sine. Differentiation of sine is cos, and using the chain rule, differentiation of at will give us a. So a cos at. So that's the differentiation. Now differentiate this once again. Okay, differentiate this once again. So d square by dt square sine of at will be equal to, again, differentiation of this. Differentiation of cos is minus sine, and chain rule, differentiate at, which will give us another a. That a and this a will give us a square. So minus a square sine at. So that's the second derivative of this function. So now let's take the Laplace transform on both sides. Okay, we'll take the Laplace transform on the left hand side, and we'll take the Laplace transform on the right hand side. So L of d square by dt square of sine of at is equal to minus a square Laplace transform of sine at. Actually, we have taken Laplace transform on the entire function, but because of the linearity property, this constant minus a square is going to come outside. So we'll have L of sine at. So now we can just apply this over here, because this is the Laplace transform of the second derivative, right? Left hand side, Laplace transform of the second derivative. This is the Laplace transform of the second derivative. So we can just expand it using this. So Laplace transform of the second derivative is s square into Laplace transform of the original function, s square into Laplace transform of the original function sine at, minus s into the value of the function at 0, s into sine of 0, minus f prime. What is f prime? First derivative. First derivative is a cos at. So substitute 0 over here, so we'll get a cos 0. So this is equal to minus a square Laplace transform of sine at. So I could combine this Laplace transform of sine at and Laplace transform of sine at. I could just combine these two together. So we will get s square, and this minus is going to become plus. So s square plus a square into Laplace transform of sine at, and of course sine of 0 is 0. Okay, cos of 0 is 1. So this is going to vanish, and this minus a, when I bring it onto the right hand side, it's going to become plus a. So we'll get this. So bring this on this side, so we'll get Laplace transform of sine at to be equal to a by a square plus s square plus a square. So this is exactly the same value that we had got in the previous lecture. We had found out the Laplace transform of sine at. So we have been able to verify that we are getting the same result. So this property is really consistent with what we had discussed earlier. Okay, so next is the Laplace transform of integrals. So suppose I have a arbitrary function f of t, then we can find out the Laplace transform of its definite integral. That is, you integrate from 0 to t, and the same function, of course u is a dummy variable. Then the Laplace transform of this integral, okay, the Laplace transform of this integral, L of integration from 0 to t f of u du is equal to 1 by s into Laplace transform of the original function. This can also be very easily proved. So when I want to find out the Laplace transform, okay, Laplace transform of this integral, so what do? I fall back onto the definition of the Laplace transform. So what is the definition of Laplace transform? We have to integrate from 0 to infinity, okay, whatever is inside the bracket, that multiplied with e to the power minus st. So this integral, okay, we bring it inside this integral, okay, and e to the power minus st into dt. So now again we can use the integration by parts technique here. I'll leave it to you to figure out what is u and what is v here. So by using integration by parts, we can have this e to the power minus st. The first term will become minus 1 by s e to the power minus st 0 to t f of u du, which will evaluate from 0 to infinity, minus 0 to integration from 0 to infinity minus 1 by, okay, this should be s. Okay, please read this as s. This is not e, this is s. So 1 by s e to the power minus st f of t dt. Okay, so this is by integration by parts. So this, the first term is going to become 0. So how will the first term become 0? Because when you put the upper limit here, okay, when you put the upper limit here, so 1 by e to the power st, so 1 by e to the power infinity, which is 1 by infinity, so that is going to give us 0. So this factor is going to make this entire term 0 when you put the upper limit, and when you put the lower limit, that is 0, okay, look at the limits of the integration. Lower limit is 0, upper limit is t. So when you put t equal to 0, so we are integrating from 0 to 0. That means we are integrating from one point to the same point. That means this integral, this result, because integration is nothing but the area under the graph, right? Integration is nothing but area under the graph. So if you both the lower and the upper limits, if they are the same point, then the area under the graph will be 0. So the upper limit will make this factor 0 and the lower limit will make this factor to be 0. So overall both the terms will be 0. So this term is also going to turn out to be 0. So as a result we will be left with this. So now we have minus and minus, this gives us a plus. So 1 by s, okay, this is not e, once again this is s, so 1 by s integration from 0 to infinity f of t e to the power minus st dt. So now this we can easily recognize, because this is nothing but the Laplace transform of the original function f of t. So this gives us the left hand side is equal to 1 by s Laplace transform of f of t, so which is the right hand side. Then the next property is the substitution property. Okay, so what it says is, if capital F is the Laplace transform of small f, then if I take s greater than a, okay, some quantity value a, and for all values of s greater than a, then multiplying this original function f of t with e to the power at is the same as making a substitution s with s minus a in the Laplace transform. Okay, essentially I have a function and it has got a Laplace transform. So in the original function, if I multiply it with e to the power at, okay, in the original function if I multiply with e to the power at, that is the same as in the Laplace transform replacing s with s minus a. Okay, so that's the substitution property. So this can also be very easily proved. So Laplace transform of e to the power at f of t, okay, so this will be equal to this. All we have to do is, in that integral we just have to replace, right? So e to the power at f of t will be multiplied with e to the power minus st, and this will be integrated from 0 to infinity. And of course now we can combine these two together. So because we have e to the power at e to the power minus st, so this will give us e to the power minus s minus a into t f of t dt. So we'll now make a small substitution. The substitution is capital S equal to s minus a. So capital S, that this s minus a, we'll call it as capital S. Then we'll have Laplace transform of e to the power at f of t is equal to integration from 0 to infinity e to the power minus capital St f of t dt. So which is nothing but, this is also a Laplace transform, right? This is a Laplace transform with respect to this variable capital S, not the small s but the capital S. So capital F, capital S, f of capital S. So now what is, we substituted back, capital S is s minus a, so this is equal to f of s minus a. So this proves the left hand side is equal to right hand side. This proves the substitution property. Next let's take an example, okay, for the substitution property. Okay, let's take an example. So let us consider a function f of t equal to 1. Okay, we will use this property. So here this function f of t that we have here, the function f of t, we call it as, we take that function to be equal to the constant function 1. Okay, so if the function is constant, then its Laplace transform will be 1 by s. You can refer to my previous lecture. Over there I had shown that the Laplace transform of some constant k is equal to k by s. So if you take k equal to 1, you will get 1 by s. So its Laplace transform is 1 by s. So by substitution property, we have this Laplace transform of e to the power at f t is equal to f of s minus a, right? So f of t, okay, is 1 e to the power at, and which is equal to f of s minus a. So we have e to the power at into 1 is e to the power at. So Laplace transform of e to the power at is equal to 1 by s minus a, and this result is also something that we had derived in the previous lecture. Okay, so you can go back to this. So we are able to verify that we can also derive this using the substitution property. So I have left these two problems as exercise to you. In the previous lesson we had derived the Laplace transform of cos and the Laplace transform of sine. I want you to use the substitution property to show that the Laplace transform of e to the power at into cos kt is equal to this, and Laplace transform of e to the power at sin kt is this. Okay, of course in the previous lecture, instead of cos kt, I think we had used cos at, not k but a here, but that doesn't matter because after all they are just some constants, right? So use the substitution property to show that this will be the result of this Laplace transform. use in the same way. Okay, it just takes 2 steps to derive these 2 results. Okay, next we have the translation or the shifting property. So let capital S be the Laplace transform of small f. Okay, capital F is the Laplace transform of small f, that is f of s is equal to Laplace transform of small f of t. Then if we multiply the Laplace transform, okay, in the previous case we had multiplied the original function with e to the power minus e to the power at, right? In the previous substitution property, the original function we multiply with e to the power at and saw what was the result on the Laplace transform. Here we'll multiply the Laplace transform with e to the power an exponential function e to the power minus bs, where b is greater than 0, it is positive. Then we find that this has the effect of translating the original function to larger values. So if you multiply the Laplace transform with e to the power minus bs, this is equivalent to shifting the original function to higher values of t. So this is how the Laplace transform is going to become. So f of t minus b, the Laplace transform, earlier it was f of t e to the power minus st dt. Now it will become f of t minus b. That means you are going to higher values of t, because I have assumed b to be positive. And earlier the integration was from 0 to infinity. Now the limits of integration will become from b to infinity. So it can be easily proved, okay, because f of s is the Laplace transform of f of t. We'll again go back to the original definition. Capital F of s is equal to integration from 0 to infinity f of t e to the power minus st dt. We'll just call this equation number 1. Okay, so now what we do is we multiply both sides by e to the power minus bs. So what happens? The left hand side we have e to the power minus bs f of s is equal to e to the power minus bs integration of f of t e to the power minus st dt. So I can take this e to the power minus bs inside and combine this with the other exponential function that we have here. So e to the power minus s, I can take minus s common, so it will give us a t plus b inside. Okay, so this is what we get. So call this equation number 2. So now let us introduce a new variable z. Z is equal to t plus b. Okay, remember b is the constant here, so z depends only on t, so z is equal to t plus b. So if z is equal to t plus b, then this implies t is equal to z minus b. Okay, and if I differentiate t, that is dt, take the differential of t, that will be equal to the differential of z. So when t equal to 0, so if I put t equal to 0 here, when I put t equal to 0, z will take the value b. Okay, why am I doing this? Because I want to find out what will be the limits of the integration when I substitute these variables. So here I am integrating with respect to t, so the lower limit is 0. So when the lower limit of t is 0, the lower limit of z will be b, and the upper limit of course will still remain infinity. Okay, t, when it goes to infinity, z will also go to infinity. So equation number 2, we can write this down in terms of z. So left hand side will remain the same. The right hand side we have, because the lower limit when t is 0, z is equal to b, so lower limit will become b and the upper limit will be infinity. And f of t is equal to z minus b, so it will become f of z minus b. E to the power minus s, t plus b is equal to z, so e to the power minus sz. Okay, once again a small mistake here. I have written e to the power minus sz. Again, this is not correct. This should be e to the power minus sz. Okay, so I'll correct this in the slide. So please read this as e to the power minus sz. Okay, not e to the power minus sz. Okay, this is what happens when you are copying and pasting code in LaTeX. Okay, so e to the power minus sz dz, because dt is also equal to dz. We'll call this equation number 3. So now we will define a function. Okay, this function we call it as g of t. Okay, how is this function defined? G of t will be whenever t is less than b, it will take the value 0. Whenever t is greater than or equal to b, it will take the value f of t minus b. Okay, f of t minus b. I mean, of course here instead of z we are just z is a dummy variable, so I could as well put the t over here. So f of t minus b, it takes the value, this function takes the value, same value as whatever is the integrand here for t greater than or equal to b, and for other values it will be equal to 0. Okay, so this is how we can understand what this function is. So let's say this is the original function, this dotted line, okay, this dotted curve, this is the original function f of t. Okay, this is the original function f of t. So original function f of t, earlier at t equal to 0 it was having this value. Now what you do is you shift the function towards the right side. So how do you do that? You in the argument you write it as t minus b, f of t minus b, that is going to shift the entire function, the original function, towards the right side. That's why it's known as the shifting property. Okay, so f of t minus b will shift this entire function towards the right side. So earlier at t equal to 0, this was the value. Now at the same value, it will take the same value, not at t equal to 0, but it will take it as t equal to b. Okay, so how do you define this function g of t? For all values of t greater than b, for values of t greater than b, for these values, okay, for these values of t, for these values of t, this function will take the same value as this function, because that's why it says for t greater than or equal to b, it will be the same as f of t minus b, and this solid blue line is f of t minus b. The solid blue curve is f of t minus b. So the function will take the same value as f of t minus b, and for t less than b, it will take the value 0. So this function g of t will be like this. Okay, for small values less than b, it will be 0. For values greater than b, greater than or equal to b, it will take the same value as this shifted function, the shifted original function. Okay, so that's the this new function that we have defined over here. Okay, so here we have, okay, equation number 3. I just write down these two equations. So equation number 3, what it says is e to the power minus bs f of s is equal to integration from b to infinity f of z minus b e to the power minus sz dz, and g of t we define it like this. Okay, so if we try to integrate, okay, if we try to integrate this function g of t, if we try to integrate from 0 all the way till infinity, if you try to integrate it from 0 to infinity, the integration from 0 to b will be redundant. We really don't need this, because from 0 to b the integration is going to give us, anyway it's going to give us 0, because the function is 0 everywhere. So what is going to matter is the integration from b to infinity. So we might as well replace this lower limit with b. So this is nothing but integration from b to infinity. So this is nothing but the left hand side, this is nothing but the Laplace transform, right? That's how we find out the Laplace transform of any function. So this is nothing but the Laplace transform of g of t. This is equal to integration. So Laplace transform of g of t is integration from b to infinity. And what is g of t? In this values, for these set of values, it is equal to f of t minus b e to the power minus st dt. So we'll call this equation number 5. Okay, so we have equation 3 and equation number 5. The right hand side is the same. Okay, please again, this mistake has just got copied from one slide to the other slide, so there is no e here, so it is e to the power minus sz. Okay, so if you look at it from on both sides, so this is z is a dummy variable, so we might as well z, because we are integrating with respect to z, so we might just replace the z here with a t here, t, we put a t here and we put a t here, and these two will be exactly identical. So from equation number 3 and 5, if capital F of s is equal to the Laplace transform of small f of t, then e to the power minus bs f capital F of s is equal to the Laplace transform of g of t, because these two integrals are same, that means this must be equal to this. So that's how we have this, where g is defined in this way. So g is basically, how do you get this function g? You take the original function, you shift it, okay, towards the right side by an amount equal to b. Okay, then you take only g of t will be defined as, it will take the value 0 for t less than b, and it will take the same value as the shifted function for t greater than b, like which has been showed in this diagram. Okay, and of course, moment we have functions like this, okay, moment we have discontinuous functions like this, you recall the lesson on the Heaviside step function. A Heaviside step function is useful when you want to represent such discontinuous functions like this. So this function g of t can be represented using the Heaviside step function. So I'll leave this to you. You can verify what, just find out what is this h of t minus b. Just draw the diagram of h of t minus b. You already have the diagram of f of t minus b. Just multiply these two, you will find that will give us g of t. Okay, so you can represent this g of t. Whenever you have situations like this, you could always bring in the Heaviside step function and you can represent it like this. Okay, so we can actually put these ideas together, and this is known as the Heaviside shifting theorem. So what it essentially says is this: the e to the power minus bs. What is capital F of s? Capital F of s is a Laplace transform of some function. Okay, e to the power minus bs times the Laplace transform of a function is equal to the Laplace transform of, instead of writing g, we write it like this. So e to the power minus bs Laplace transform of some function is equal to the Laplace transform of the shifted function multiplied with the Heaviside step function. Okay, arguments remaining the same in both these functions. So that's the Heaviside shifting theorem. Okay, so we can actually use this Heaviside. One application of the Heaviside shifting theorem is to find out the Laplace transform of the Heaviside step function. Very straightforward. So the Heaviside shifting theorem, this is the Heaviside shifting theorem. E to the power minus bs Laplace transform of f of t is equal to Laplace transform of the product of f of t minus b times h of t minus b. So this is the Heaviside shifting theorem. So let's say f of t is equal to 1. Okay, this function. Okay, we'll take this function as 1. So if this function is 1, then the Laplace transform of this function will be equal to 1 by s, of course. Okay, when this function is 1, then the value, so because f of t is 1, that means it's constant everywhere, right? The function is constant everywhere. So if you shift the function towards the right or towards the left, doesn't matter. Okay, so I shift the function towards the right, the function will still remain a constant. So f of t is equal to 1, that means f of t minus b is equal to also 1. Okay, and of course the Laplace transform of this function is equal to 1 by s. So f of t we have already seen. Okay, if f of t is k, the Laplace transform is k by s. So if I take k as 1, f of t equal to 1, the Laplace transform will be equal to 1 by s. So we have already found out this one in the previous lecture. So just put these together in the Heaviside shifting theorem. So Heaviside shifting theorem, this is what it is. So what we do is e to the power minus bs, okay, Laplace transform of the original function. The function is 1, so its Laplace transform will be equal to 1 by s, into is equal to Laplace transform of f of t minus b will also be equal to 1 because it's a constant function, it really does not matter, into h of t minus b. So this gives us the Laplace transform of the Heaviside step function h of t minus b is equal to 1 by s e to the power minus bs. What about h of t, Laplace transform of h of t, where b is equal to 0? In that case, 1 by s e to the power minus 0, okay, which will be equal to 1. So it will be simply 1 by s. So Laplace transform of the Heaviside h of t alone will be equal to 1 by s. If h is has got a shift, okay, h of t minus b, then it will be 1 by s e to the power minus bs. So that's the one application. You can use the translation or shifting property to find out the Laplace transform of the Heaviside step function as well. Next we have this change of scale property. So if f of s is the Laplace transform of capital F is the Laplace transform of small f, okay, that is, we can write it like this, then for any any positive a, the Laplace transform of f of at, that means it's not we are not taking the function. So it means suppose t was taking values 0, 1, 2, 3, 4 and so on, and let's say a is equal to 2. So the this function will we are evaluating at 2 times the whatever the values of the function are. So basically you are just increasing the scale, right? Or it's like zooming in to the function. Okay, that will be equal to 1 by a times the Laplace transform, where the argument becomes, instead of s, it becomes s by a. This can also be very easily proved. So we start with the basic definition of the Laplace transform. So L of f of at is equal to integration from 0 to infinity e to the power minus st f of at dt. So now what we do is we do a little bit of manipulation here. So e to the power st, that this one we multiply and divide by a. Okay, so this e to the power st we multiply and divide by a. F of at will keep it as it is, and d of t, okay, dt, this t we write it as at by a, because multiply and divide by a. Okay, and then we rearrange these terms. So this 1 by a is anyway constant, so this 1 by a I could bring it outside. Integration from 0 to infinity e to the power minus, okay, this 1 by a I combine it with s, so e to the power minus s by a, and this a I am combined with t, so at. Okay, this 1 by a I combine with s, so it will become s by a, and this a in the numerator will go with t, so it will give us at, f of at, and of course this 1 by a, it has come outside, so what is left behind is at. Make some substitution here. We call tau as at. Okay, this product at we call it as tau, and this quantity s by a we call it as capital S. Substitute this back over here. In this equation we have Laplace transform of f of at is equal to 1 by a integration from 0 to infinity e to the power minus this s by a is capital S and a tau is at is tau, so this will give us s tau f of tau d tau. Okay, and we realize that this is also nothing but this is how we can express the Laplace transform, because tau is anyway a dummy variable, so this is nothing but the Laplace transform, the Laplace transform of f of tau. So this is nothing but the Laplace transform of f of capital S. Okay, so Laplace transform capital S, 1 by a Laplace transform capital S. Now substitute this tau and s everywhere, so this will give us L of f of at is equal to 1 by a f of s by a. So this is basically the change of scale property. Next property is the derivatives of Laplace transform. So we already have found out how to find the Laplace transform of derivatives. Next, how to find out the derivatives of Laplace transform. Okay, so Laplace transform of derivatives we already found out. Now how to find out the derivatives of the Laplace transform. So here what you do is, here you first find out the derivative, then you do the Laplace transform. Here you first find out the Laplace transform and then you find out the derivative. So if f of s is the Laplace transform of f of t, capital F is the Laplace transform of small f, then the nth derivative of this Laplace transform is obtained in this way. Okay, the nth derivative is obtained in this way. The nth derivative of capital S times minus 1 to the power n is equal to the Laplace transform of t to the power n f of t. Now this result is extremely useful. We will not be proving this result, but we will be using it in some applications. So for instance, let's say I want to find out the Laplace transform of this function, that is t e to the power kt. Okay, f of t is t e to the power kt. I want to find out the Laplace transform of this one. Then f of t is equal to, let's say we'll take a function. Okay, actually I should have used a different symbol here, but I mean you get the idea. This f of t and this f of t are not the same. It's f of t because I want to apply this directly in this expression. Okay, so f of t is equal to, let's say, e to the power kt. This e to the power kt, we'll just call it as f of t. Then we already know, in the previous lecture we have already found out, right, the Laplace transform of e to the power kt, which is equal to 1 by s minus k. That is the Laplace transform of e to the power kt. So when you differentiate this differentiation, that is df by ds is equal to minus 1 by s minus k whole square. Differentiation of this with respect to s will be minus 1 by s minus k whole square. So for n equal to 1, okay, this formula, for n equal to 1, the Laplace transform of, what will this become, n equal to 1. So we have t f of t, Laplace transform of t f of t is equal to minus 1 to the power 1, so which is going to give us a minus sign. D n is 1, so df by ds. So L of t f t is equal to minus df by ds. So when you substitute over here L of t, right, f of t is equal to e to the power kt. So L of t e to the power kt, L of t e to the power kt is this, it is equal to minus, and this minus will give us a plus, so 1 by s minus k whole square. So s is greater than k. Where we get this? We get this because of the condition, right, this condition. Okay, the condition for the Laplace transform, the same condition will hold good here as well. Okay, so this is how you find out the Laplace transform functions like this using the derivatives of Laplace transform formula. So I'm leaving these to you as assignments. You can try this out. Okay, so find out the Laplace transform of t cos kt, t sin kt, t hyperbolic cos kt, and t hyperbolic sin kt. Okay, you already know what is the Laplace transform of, let's say, cos. Okay, then you can just use this formula to find out the Laplace transform of t cos kt. Then we have the integrals of Laplace transform. Again, we will not be proving this property, we will just be it's important that you just know what this property is. So if capital S is the Laplace transform of small s, then the definite integral of capital F, the Laplace transform from b to infinity, is obtained in this way. Definite integral of the Laplace transform from b to infinity is obtained as the Laplace transform of the function divided by t, provided of course this quantity, the limit exists, because if if this becomes undefined, there is a good chance that this will become undefined, because at t equal to 0 this quantity may become undefined. So we have to make sure that the limit of this quantity, at least it exists as t tends to 0. Finally, we have the convolution property. Remember, we had discussed convolution in one of my earlier lectures. So we could talk about the convolution property. Again, this the proof of this is not required because that is that is at the postgraduate level. So here you are just required to know the statement of the convolution property. So this convolution property, we can also write this as a theorem. It's known as the Laplace convolution theorem or the Falton theorem. So what basically it says is this, okay. So the Laplace transform of the convolution of two arbitrary functions, that is, I have one function f1, another function f2. These are two arbitrary functions, and I want to find out the convolution of these two functions. So f1 star f2. So this is the convolution of these two functions, and if I take the Laplace transform of this convolution, so the Laplace transform of the convolution of two arbitrary functions is equal to the product of the Laplace transform of the two functions. So take two functions, the convolution of two functions, find out its Laplace transform. That is the same as find out the Laplace transform of the first function, find out the Laplace transform of the second function, and just multiply them together. So that's your convolution property. So this brings me to the end of this lecture. So here I have just put all the questions that I left to you as assignment. I just put together in one slide. So please do these problems at home, and yeah, these are two more problems. So these are what I had given in the slide so far, and these are two extra problems. Find the Laplace transform of the square pulse, okay, which is given by this one. Okay, find out the Laplace transform of the square pulse, and find out the Laplace transform of the Dirac delta function. So I would like to leave this to you. Okay, you can try it out. You just have to use the definition of the Laplace transform, and you can easily find out the Laplace transform of the square pulse and the Laplace transform of the Dirac delta function. So please do these problems at home, and in case you have any queries, so please get in touch with me. So all the best. Thank you.